The evolution of chemistry spans millennia and is a complex journey, influenced by various cultures, thinkers, and technological advancements. Here's a detailed account of the major milestones in the evolution of chemistry from ancient Greece to modern times. Ancient Greece 600 BC, 300 BC. Greek philosophers such as Thales, Anaximenes, and Empedocles speculated about the nature of matter. They proposed that the universe was composed of fundamental elements like earth, air, water, and fire. Democritus introduced the concept of the atom, suggesting that all matter is composed of indivisible particles called atoms. Alchemy 300 BCE, 1600 CE. Alchemy originated in Hellenistic Egypt and later spread throughout Europe, the Middle East, and Asia. Alchemists aimed to transmute base metals into gold, discover the philosopher's stone as substance, believed to grant immortality, and create the elixir of life. Despite its mystical goals, alchemy laid the groundwork for experimental methods and contributed to the development of laboratory equipment and techniques. Islamic Golden Age 8th, 14th century. Muslim scholars such as Jabir ibn Hayyan Gabr made significant contributions to alchemy, including the development of laboratory techniques, distillation apparatus, and chemical processes. They translated and preserved ancient Greek texts, including those of Aristotle and other Greek philosophers, which later influenced European alchemy. Early modern period 16th, 18th century. The Renaissance brought about a resurgence of interest in science and empirical observation. Paracelsus rejected the mystical aspects of alchemy and emphasized the importance of observation and experimentation in medicine and chemistry. Robert Boyle's work laid the foundation for modern chemistry with his experiments on gases and the formulation of Boyle's law, which describes the relationship between pressure and volume of a gas. Antoine Lavoisier is considered the father of modern chemistry for his discovery of the law of conservation of mass and the identification of oxygen as a key element in chemical reactions. His work led to the development of the modern chemical nomenclature and the concept of chemical elements. 19th century. John Dalton introduced the atomic theory, proposing that elements are composed of indivisible particles called atoms, each with its own characteristic mass. Dmitri Mendeleev developed the periodic table, organizing elements based on their atomic masses and properties, and predicted the existence of undiscovered elements based on gaps in the table. The rise of organic chemistry led by Friedrich Ler and others demonstrated that organic compounds could be synthesized from inorganic substances, debunking the notion of vitalism, the idea that organic compounds could only be produced by living organisms. 20th century to present. The development of quantum mechanics revolutionized our understanding of atomic and molecular structure, leading to advancements in spectroscopy, molecular orbital theory, and chemical bonding. The discovery of radioactivity by Marie and Pierre Curie, and the subsequent work of Ernest Rutherford and others laid the groundwork for nuclear chemistry. The synthesis of complex organic molecules, advances in polymer chemistry, and the development of computational chemistry have all contributed to the diverse field of modern chemistry. Throughout its history, chemistry has evolved from mystical and philosophical beginnings to become a rigorous scientific discipline based on experimentation, observation, and theoretical understanding. Today, chemistry plays a critical role in various fields, including materials science, pharmaceuticals, environmental science, and energy research. The period from the 1850s to the present day witnessed a remarkable revolution in the field of chemistry, marked by groundbreaking discoveries, technological advancements, and paradigm shifts. Here's an overview of the revolution of chemistry during this time. Organic chemistry in the mid-19th century. Organic chemistry experienced a significant transformation with the synthesis of organic compounds from inorganic sources, challenging the concept of vitalism. Friedrich Wöhler's synthesis of urea from ammonium cyanate in 1828 is often regarded as the starting point of modern organic chemistry. The elucidation of molecular structures by chemists like August Keckel and Archibald Scott Coeur, and the development of structural formulas, paved the way for the systematic study of organic compounds. Periodic table and chemical binding. Dmitri Mendeleev's publication of the periodic table in 1869 provided a systematic framework for organizing elements based on their atomic masses and properties. His table accurately predicted the properties of yet-to-be-discovered elements, the discovery of valence, and the development of chemical bonding theories, including Lewis structures and molecular orbital theory, revolutionized our understanding of how atoms combine to form molecules. Industrial chemistry and catalysis. The Industrial Revolution fueled advancements in chemical manufacturing, leading to the production of fertilizers, synthetic dyes, explosives, and pharmaceuticals on an industrial scale. The development of catalysis, particularly through the work of Wilhelm Ostwald and Fritz Haber, played a crucial role in increasing the efficiency and selectivity of chemical processes. Physical chemistry and thermodynamics. The emergence of physical chemistry as a distinct discipline in the late 19th century integrated principles from physics and chemistry to study the underlying physical properties and behavior of chemical systems. The formulation of the laws of thermodynamics by scientists such as Josiah Willard Gibbs and Svante Arrhenius provided a theoretical framework for understanding chemical reactions and equilibrium. Quantum mechanics and spectroscopy. The advent of quantum mechanics in the early 20th century revolutionized our understanding of atomic and molecular structure, paving the way for advancements in spectroscopy and quantum chemistry. Quantum mechanics allowed for the calculation of electronic structure, molecular energies, and chemical properties, enabling scientists to predict and interpret experimental data with unprecedented accuracy. Modern analytical techniques. The development of sophisticated analytical techniques, including chromatography, mass spectrometry, nuclear magnetic resonance, NMR, spectroscopy, and X-ray crystallography, revolutionized chemical analysis and characterization. These techniques allowed chemists to identify and quantify compounds with high precision, elucidate molecular structures, and study chemical reactions in real time. Materials science and nanotechnology. The 20th century saw significant advancements in materials science and nanotechnology, driven by discoveries such as the development of synthetic polymers, semiconductor materials, and carbon-based nanomaterials like graphene and carbon nanotubes. These advancements have led to the creation of novel materials with tailored properties for applications, ranging from electronics and energy storage to medicine and catalysis, green chemistry, and sustainability. In recent decades, there has been a growing emphasis on green chemistry principles, aimed at minimizing the environmental impact of chemical processes and products. Sustainable synthesis methods, renewable feedstocks, and the design of environmentally benign catalysts have become central to modern chemical research and industry. Overall, the revolution of chemistry from the 1850s to today has been characterized by interdisciplinary collaboration, technological innovation, and a deeper understanding of the fundamental principles governing chemical phenomena. These advancements have not only transformed the field of chemistry, but also had profound impacts on numerous aspects of society, from healthcare and energy to materials and the environment.